Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. We've mastered the first derivative, which is the slope. But what happens if we take the derivative of the derivative? Welcome to higher order derivatives. Before we get started, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. Now suppose that f is a differentiable function. Then the second derivative of f is the derivative of f prime being the first derivative of our function f. And just like the first derivative, there are many different ways of writing this. We have f double prime of x, which is the second derivative of our function f, or y double prime, meaning the second derivative of y, or in Leibniz notation, it's written as d squared y over dx squared. Notice how these squares are in different places. And that's because we're applying the operator d by dx twice. And we're applying it twice on our y. So that's why it's d squared y over dx squared. And similarly, if we want to take the nth derivative, it can be written as f, and then we have this n in the power, but with brackets, of x. And then in Leibniz notation, this would be d to the power of ny over dx to the power of n. And now let's take a look at how to find the second derivative with an example. So using the definition, we know that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. So now if our function f of x is equal to x squared minus 2, this is going to be equal to the limit as h approaches 0 of x plus h squared minus 2. So that's our f of x plus h. And then minus f of x. So that'll be x squared minus 2. And then our denominator here is just h. So let's go ahead and expand out the first bracket. So we get limit as h approaches 0, and then this is going to be x squared plus 2xh plus h squared minus 2. And then let's go ahead and distribute this minus, so we get minus x squared plus 2. And then our denominator here is still h. So let's take a look at what we can cancel out on top. We have a minus 2 and a plus 2, so that cancels. And then we have a positive x squared and a negative x squared. So that also cancels, which means we're only left with 2xh and h squared, both of which have an h in there. So we can go ahead and factor that out. So this is limit as h approaches 0. And then we're going to get h times 2x plus h over h. And now we can cancel out the h on the top and on the bottom, and then do our direct substitution. So this ends up being equal to 2x. So this is our f prime of x, which is the first derivative. And now to find the second derivative, we just have to do this all over again. So f double prime of x is going to be equal to the limit as h approaches 0. But now the function that we're using is f prime of x instead of f of x. So this is going to be f prime of x plus h minus f prime of x over h. So substituting our function in, we get 2 times x plus h minus 2x over h. Okay, so let's go ahead and simplify our numerator. We get 2x plus 2h minus 2x over h. Now we cancel out the 2x, and then we cancel out the h on the top and the bottom, and this ends up being just equal to 2. So therefore, the second derivative, f double prime of x here, is equal to 2. So why is it that we care about the second derivative? Well, I think physics would give us the best answer. So let's say we start with our basic function, f of x. And a lot of times in physics, we would write that as s of t. And it's just a different way of naming our function. So this base function is your position, meaning where are you? Now when we take the first derivative, that's going to be f prime of x. That is equal to the velocity because it is how fast your position is changing. And in physics, we usually call that v of t to stand for velocity. And now the second derivative is going to be f double prime of x. And what that stands for is acceleration. And that's because it measures the change in velocity. And we usually write that as a of t to stand for acceleration. So imagine you're sitting in a car and you're driving at some speed. And then you're going to push the gas pedal in the car. And when you do that, you're changing your velocity. And the feeling of being pushed back into your seat, that's the second derivative in action. And it doesn't stop there. There are actually further derivatives that exist in this context. If you're interested, you can look up jerk, snap, crackle, and pop for higher derivatives in kinematics. Next, we're going to take a look at an example where we have three graphs that are drawn on the screen here. One of them is the position, another one is the velocity, and then the third one is the acceleration. And we want to identify which one is which. So there are multiple different ways of doing this, but what I like to do is I like to take a look at the graphs and identify if each graph has a point where we have a horizontal slope. And the reason I do that is because I find it easier to spot. So let's say we have our red curve, we'll call that y1. We'll call the green one y2, and then we'll call the blue one y3. So here I can notice that y1 maybe starts off with a horizontal slope. And then y2 has a horizontal slope right over here. And then y3 has a horizontal slope right over here. So what I'm going to do next is I am going to find the x value of each of them. So that would be right here for y2, right here for y3, and then right here for y1. So now the reason I do that is because if I look at y2, y2 has a horizontal slope at this x value, which tells me that the derivative of y2 must equal 0 right over here. But neither the red nor the blue graph crosses 0 there. So that tells me that neither y1 nor y3 are the derivative of y2. Now y3 has a horizontal slope at this particular x value. And then we can see that y2 has a value of 0 right over there. So that means I want to check that maybe y2 is the derivative of y3. And I'm going to put a question mark there because right now I've only checked this one particular value. I want to look at the entire graph to make sure that that's true. So let's take a look at that next. So looking at our y3, we can see that we start off with a very negative slope, and then it gets a little less negative until we hit this x value. So that matches what we see on y2 because we start with a really negative y value, and then it gets a little less and less negative until we hit this value, which is 0. And then afterwards, we can see that we start getting a positive slope, but it's a small positive slope until we hit around here, which is more positive, and then it kind of flattens out a little bit. So it's still positive, but it gets a little bit less and less and less positive. And we can see that that's exactly what y2 is showing us. So here we're positive, and then we get more positive until we hit around this area where it's the most positive, and then it starts being a little less and less positive, but it's still positive. So now I'm confident to say that y2 is the derivative of y3. And next we can see that for y1, we start off with a horizontal slope. So that tells us that maybe y3 is the derivative of y1. So for y1, we can see that we start with a 0 slope, and then it's negative slope afterwards, but it's a small negative number, and then it maybe gets a little bit steeper, a little bit steeper, a little bit steeper, and then afterwards, it's still negative, but then it gets less steep. So the slope of y1 is always negative, starts off a little less steep, gets more steep, and then becomes a little less steep again. So that matches what we see for y3, because y3 is always negative. We start with 0, and then we go from a small negative number to a more negative number, and then we go back to being smaller negative numbers. So therefore, y3 is the derivative of y1. So from these two, we can see that we start with y1, and then we would have y3 is the derivative of y1. And then since y2 is the derivative of y3, that tells us y2 is the second derivative of y1. So now matching this with our position, velocity, and acceleration, we would have our red curve is the position, so that'll be s of t. y3, which is the blue curve, that is going to be the velocity, so that'll be v of t. And then the green curve is the second derivative of y1, so that is going to be the acceleration, which is a of t. Lastly, did you know that there is actually a way to skip the middle step and find the second derivative directly? So the limit definition for the second derivative is shown on the screen here. Now at first glance, it looks intimidating, but it's actually a beautiful symmetric formula. And we'll dive deeper into where this comes from in a future video if you're interested. So let's try using this definition to find the second derivative of f of x from above. So we would get f double prime of x is equal to the limit as h approaches 0 of f of x plus h, so that'll be x plus h squared minus 2. And then we have minus 2 times f of x, so that'll be 2 times x squared minus 2. And then we have plus f of x minus h, so that's going to be x minus h squared minus 2. And then we have all of this over h squared. So now we just need to go ahead and expand the brackets on top. So we end up with x squared plus 2xh plus h squared minus 2. That's the first bracket. The second one, once we distribute our negative, is going to be minus 2x squared plus 4. And then the third bracket, that's going to be x squared minus 2xh plus h squared minus 2. Okay, and then this is over h squared. And now we can see that there's going to be some cancellations on top. We have an x squared plus an x squared minus 2x squared. So that means these three are going to cancel out. We have a plus 2xh and a minus 2xh. And then we also have a minus 2, and a plus 4. So they get canceled to 0, which means we're only left with h squared plus h squared, which is 2h squared. And since 2h squared over h squared is just equal to 2, we get f double prime of x is equal to 2. And now let's do a quick recap of what we covered in this video. We saw that derivatives don't stop at the first one. Taking the derivative again gives us the second derivative, which measures how the rate of change itself is changing. We learned that higher order derivatives have real meaning. In motion problems, position leads to velocity, and velocity leads to acceleration. And higher derivatives describe even more subtle changes in motion. We looked at 2 different ways of finding the second derivative. We applied the limit definition of the derivative twice, and we also used that single symmetric limit formula to jump directly to finding the second derivative. And finally, we looked at an example of how to identify the graphs of f, f prime, and f double prime. Understanding how slope and curvature relate lets you identify each graph visually without doing any calculations. And now it is your turn to give this a try. Can you find the solution to this problem on the screen here? Make sure to leave your answer in the comments below and let us know what other calculus topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, Make sure to drop it in the comments.